Last session, we started with natural language processing and in particular, language modeling. We said that language modeling belongs to the category of pre-training fine-tuning, and that is basically what is called transfer learning, pre-training fine-tuning. We have large corpus of unlabeled data. We want to learn something on them and then transfer them to a task that might end up having less data. And these tasks are usually called downstream tasks. And we saw this idea before, even when we were doing word representations, we were doing transfer learning. We were learning something from unlabeled corpus, and that something was basically our word representations. Turn each word, each ID of your words in your dictionary or your vocabulary to vectors, associate meaning to them, and then transfer those word vectors to other downstream tasks. Maybe you want to do sentiment analysis later on. So that was the idea. But with that framework, you could only associate a single vector to every single ID or word in your vocabulary. If you incorporate the context, you're going to be able to associate multiple meanings to the same word according to the context. For instance, play here could end up having two different meanings or multiple different meanings depending on the context. That's the idea of LMO. And we were using recurrent neural networks and LSTMs for LMO for this model that I'm covering, that I covered last session. We were doing temporal convolution, and to make convolution suitable for temporal type of data, like sequences or text, you need to make some modifications. One is this causality constraint, so that you're always looking in the past. There is this other idea of dilated convolution, which is going to enable you to go further and further in the past and recall information from long time ago in your sequence. And then we continued with transformers. We saw transformers and attention mechanisms when we were doing translation. We can actually use transformers to do language modeling, to do the task of next word prediction. Given the past, predict the future. This probability is the only thing that's changing, the model that you're writing. It could either be an LSTM, it could be CNNs, or it could be transformers. And one good thing about transformers is that they have very little inductive bias in them, unlike CNNs and RNNs. And that's why transformers are going to let your data speak. And that's why you use them for the task of pre-training, because you have a lot of data. Let's learn all the nuances of a language and encode them in a transformer architecture. And then you can do downstream tasks with modifying the head of your transformers. Any questions about it? Okay, in that case, we can move on. For this architecture, we are using the masked multi-head self-attention. And if you remember the translation architecture, the original transformer, you have an encoder block, and then you have, or multiple encoder blocks, and then you have multiple decoder blocks. And the only difference is that one of them is masked, the other one is not masked. And it is masked because you want to take into account the past and not the future. Don't look into the future. And that constraint is only because the way that we are writing our loss function or our likelihood. If you change your likelihood model, probably you're going to be able to use the encoder part of the transformer. And that's exactly what Bert is about. So this is an assignment for you to watch the corresponding video for this slide. I'm not going to spend too much time on it, but I can give you the big picture and then you can ask questions. It is still the same paradigm as before. You're going to be doing transfer learning, pre-training, fine-tuning. For pre-training stage, you have plenty of data on labeled corpus in front of you. For fine-tuning, you have a downstream task. That downstream task needs to have labeled data. Labeling requires human, and therefore you're going to end up with fewer data, unless the labeling itself is an easy one, like labeling images. But this is not the case for language. What is Bert doing? Let's focus on the pre-training stage. Unlike the task of predicting the next word, you are going to take the entire sequence as an input. You are going to noise it or add noise to it. It means that you're going to mask 15% of your word pieces. And we know what word piece is. It's a generalization of byte pair encoding. You're using a different merging strategy to merge your subwords. But this is going to give you a subword tokenization process. You mask 15% of those tokens in each sequence at random. And then there's also some minor details that I'm going to go over them when we cover next papers. But as long as the big picture is concerned, you're going to mask 15% of your sentence. Or it's not a sentence, let's call it a sequence. There is also another part to your loss, and that's about next sentence prediction. What is that and why would you do that? Because for some of your downstream tasks, like question answering or these types of sentence pair classification tasks, is this the next sentence that is following the previous sentence? Is this a natural entailment or is it a contradiction or is neutral? Because of those sorts of tasks, which take as input pair of sentences, you're going to think of the idea that maybe during pre-training, it's a good idea to do the same thing. Take pairs of sentences as input and separate them using a separator token. And then what is this task 2 doing? While you're doing your training, you look at this classification head or you look at this classification token. And then we know that a transformer is going to take a sequence as input. It's going to output another sequence. And then you look at the first entry of your output. It's going to be a vector of the dimension that you chose for the hidden dimensions of your transformer. You need to adjust it because in the end, it's a binary classification task. You can output either a single number or 2 numbers. If you output a single number, you're going to put a sigmoid on it. If you output 2 numbers, you're going to put a softmax on it. How do you train this? While you're sampling sentences, the next sentence could be in the same paragraph as sentence A. So sentence A and B could end up being in the same paragraph. This is the way that you're going to sample them for the positive case. For the negative cases, sentence B is taken at random from your corpus, from somewhere in your corpus, some other document. Or it could be the same document, but a sentence that is far away. It's not the immediate next sentence. So that's this part. You're going to write a loss function and you know how to train that. For the masked portion, maybe one of these tokens ended up being masked. You take that masked token, push it through the architecture, and in the end, you're going to get the corresponding vector, but your task is predict that word. What did I mask? And then this is going to be a classification over the size of your vocabulary. Out of these tokens, which one is the correct token that we masked? There are also some other details here. In addition to positional embeddings and token embeddings, which are just vectors per each word, and these are vectors per each index, you're going to have a segmentation embedding. You need to know, is this sentence A, and where does it end, and is the rest of it sentence B? So that's the way that you're going to encode it. And then you do your pre-training. So what I just explained was this part of the pre-training process. Any questions about that?
If you're minimizing kind of 2 parts to the loss function, depending on the downstream task, is there any benefit to only minimizing 1 part of the loss function if you know what the downstream task is going to be?
So at this stage, during the stage of pre-training, you want to have a generic model that can be adapted quickly to your downstream tasks. So at this point, you want to be as general as possible. And that's why when you look at some of these downstream tasks, they depend on pair of sentences, like question answering and this other guy. Therefore, you include this as part of your loss function during pre-training. So please don't confuse this. You are not going to actually focus on the task of question answering or next or natural language inference. You are not focusing on that during the pre-training. During pre-training, you are just asking a simple question. I'm going to give you 2 sentences. Are they natural follow-up on each other, or sentence B is from a totally different corpus. Does that answer your question?
Yeah, sorta. I guess I'm wondering more if you wanted to have the best sentence answering model in the future, would it be better to use one of these generally trained pre-language models or just almost specify all the training towards that task if you're trying to get like state of the art best in class type of model?
That's actually a good question. Uh, and there is pros and cons to each one of these approaches. Let's take the case that you know exactly what you want to do, which is natural language inference, and then you're gonna create a dedicated model for it. And this is exactly what we have been doing so far. We had the task of sentence classification, and we were designing our architectures for that particular task. So it was task-specific architectures like CNNs or even that tree-based architectures that we were coming up with, recursive type of models. That we have been doing, but we saw a drawback there. And the thing is, you couldn't enlarge your model because you had only a handful of data. And by a handful, I mean 1,000 or even 1,000,000 data, which is definitely not enough to train larger and larger models. So you have to be smart about the architecture, the way that you train it. You have to put more inductive bias in your architecture. What we are doing here with pre-training fine-tuning, you're going to say that you are not limited to the data that is available to you for that downstream task. Why? Because for language, you have plenty of unlabeled data. Can you use that and train larger and larger models? And that's the idea here. With pre-training, fine-tuning, you're going to write a generic model, you're going to write a generic loss function, you learn something, and then you transfer it to downstream task. And because this model has seen a lot of data, first of all, it's not going to overfit on the pre-training task. No model is large enough to learn the entire internet. So it's not going to overfit. And at the same time, because it learned something about human language in its weights and biases, it's going to be very good at solving downstream tasks with a few modifications, maybe change the head. And this is beautiful. And you're going to be the state of the art. And that's why BERT, GPT type of models are really famous because they are useful. But there's a downside to it. Nothing is for free. The downside is these models are going to end up being large. And if you want to use them in production for a task as simple as doing sentiment analysis, probably you don't need such a large model when it comes to production. And there are actually ways of mitigating that problem when it comes to BERT. There is this idea of distillation. You're going to distill the knowledge that you learned through pre-training in a smaller model. And that's called distill BERT. We are going to cover that. But it's always a good thing. The more data you have, the more your neural network is going to like it. And the larger models you can train. And at the same time, sometimes your thought process is not having something to put in production all the time. Sometimes you want to go towards artificial general intelligence or human level intelligence. And if you think about how a human learns for the first few years of our lives, when we are born up until we open our mouth and speak, we are just learning on our own from our parents, from our environment, by the task of listening and learning. And suddenly we are going to open our mouth and then start speaking. Initially, we are going to be really bad. And then our parents are going to correct us. And then that's going to end up being the fine-tuning part. We start mispronouncing words, misplacing them, and then somebody corrects us. And then we start speaking. It's the same process here. Did I answer your question?
Yes, thank you.
Yeah, sure. The idea is that a human that knows about language, it's going to easily adapt to different tasks. Can we do the same thing? We can easily do natural language inference. We can easily do sentiment analysis. We can easily find the correct portion of a paragraph that answers a particular question. Or we can just look at a sentence and say, this word corresponds to a person. That other word corresponds to an organization, etc. And we are capable of learning from very few data but maybe behind the scene, there was some pre-training going on. Maybe that pre-training is part of us learning on our own, or that could be passing on from one generation to the next generation. Whatever that our parents learned are gonna pass to us through instincts. And maybe that's why we are really fast at learning new tasks. So that's the idea. What else? That was about pre-training. For fine-tuning, you need to make some modifications. If your task is natural language inference, I give you two sentences. Are they following each other? Are they contradiction? Are they neutral with respect to each other? The only thing that you need to change, you keep all of these weights, the entire architecture the same. You just change this head. That's the only modification that you change, that you do. And because these are initialized randomly, you can do fine-tuning. And because these are very few parameters, whenever you have very few parameters, you need less data to learn them. Similarly, for sentence classification, semantic analysis, some question answering type of problems. The other one is this question answering, where somebody asks a question, and then you are going to go in a paragraph and then find the sentence or a couple of sentences that are actually the answer to this question. So make sure that you're going to do an exploratory data analysis on SQuAD, Stanford Question Answering Dataset. And all you are doing is modifying the head of your architecture a little bit. And we covered named entity recognition previously. Any questions about the fine-tuning part or BERT in general? The question is, could BERT be adapted to output a sequence? I think I can interpret your question in two different ways. It is already outputting a sequence, but if your question is, can it output a sequence of a different length? The answer is yes, and that one we are going to cover later on. We are going to modify BERT to do that. And that's where you're going to bring back those ideas of encoder decoder. And it's going to become very similar to translation. Yeah, exactly. At this point in time, BERT cannot do translation because you might end up with a sequence that is either shorter or longer than the target translation. But we are going to see some architectures that do that. That's a very good question. Any other ones? Okay, perfect. If there are no more questions from BERT, we can continue.